In this video, we're finally going to get to the actual limit definition of continuity. And to be continuous to a point, what we mean is this. So I'll say f of x is continuous at x equals some x value, x naught, if and only if the limit as x approaches x naught of f of x is equal to f of x naught. And put more simply, it is continuous if the limit equals the value. Now, considering our discontinuities, if I had a removable discontinuity, like this, a whole, the limit would equal something, but it would have no value. If I had a jump discontinuity, I have a limit that does not exist, so that couldn't work. If I have an infinite discontinuity, even if the limit exists, I can't have a value equal to infinity because these are real valued functions we're considering and infinity is not a real number. And if I had an oscillating discontinuity, I don't have a limit to be equal to something. If the limit does not exist, it can't possibly be continuous. So let's look at a couple examples. First example, we have this piecewise function. And here's how I'm going to deal with this. First off, I need to find the limit. So I'll consider the limit as x approaches 2 from the left of f of x, which will equal the limit as x approaches 2 from the left of this function, because as I'm left of 2, this is the one that makes the difference. And as x is approaching 2, x plus 3 is approaching 5. If I had the limit as x approaches 2 from the right of f of x, that's going to equal the limit as x approaches 2 from the right of 7 minus x squared, which will end up equaling 3. Since these do not equal the same thing, the limit as x approaches 2 of f of x does not exist, and therefore cannot equal the value. So f of 2, I put the 2 into this function, equals 3. And so the answer is no, it is not continuous. If, however, this were a 9, so let me talk about it. If this were a 9 minus x squared instead of a 7 minus x squared, then this would be 5. And then the limit as x approaches 2 of f of x would equal 5, which would also equal f of 2. And in this case, the limit did equal the value. So if I changed it here, it would be continuous. All right, 2 more examples. Now, here's the nice thing about this. If I know a function is continuous, I can just put in this target x value and I'll get the limit, because a function will be, the limit will equal the value when it's continuous. And I also know, so polynomials are continuous on all real numbers. Anywhere you go, polynomials work. So do sine and cosine. So do exponential functions. And there are others. There are many functions that work a lot of the time, and the ones we're considering here are rational functions. And these are continuous so long as the denominator does not equal 0. So let's consider this one. If I put 3 into the denominator, 3 squared is 9, times 3 is 27, minus 48 is most certainly not 0, so I can just put in the 3. This will be continuous at x equals 3. So the limit will equal the value, 2 times 3 squared minus 4 times 3 minus 16, all over 3 times 3 squared minus 48. Now let me do this carefully because I'm bound to mess up. 3 squared is 9, times 2 is 18. Minus 12 is 6. Minus 16 is negative 10. 3 squared is 9, times 3 is 27. 48 minus 27 is 21. Sorry, 27 minus 48 is negative 21. And so I get 10 over 21. Now this other one's a little bit different, and here's a nice little trick for these. Okay? If I put the 4 into the denominator, 4 squared is 16, times 3 is 48, 48 minus 48 is 0. So this is not continuous. So it is not continuous at x equals 4, where it is continuous at x equals 3. So I can't just put in the 4 here, but what I can do is I can factor this out and try to reduce it out. So this will equal the limit as x approaches 4 of, I can factor a 2 out, and if I take out the 2, that's going to leave me with x squared minus 2x minus 8, so that factors as x minus 4, x plus 2. And in the denominator, I can factor out a 3. That would leave me with x squared minus 16, so that leaves me to x minus 4, x plus 4. And here's what happens. The x minus 4's cancel. Now, I'm going to write a little aside here. It's worth noting that 2x squared minus 4x minus 16 over 3x squared minus 48, our original function here, is going to equal 2 times x plus 2 over 3 times x plus 4 everywhere that x does not equal 4, because this is undefined at 4, so this must be undefined at 4. But here's the thing. This is the limit as x approaches 4. I don't care what happens at 4, I just need to figure out what happens close to 4. So this here is continuous at 4, the 2/3 and the x plus 2 over x plus 4, and I can just put the 4 in now because I've sort of extended this function by getting rid of the whole. And so I get it equal to the value of 2 times 4 plus 2 over 3 times 4 plus 4. 4 plus 2 is 6 times 2 is 12. 4 plus 4 is 8 times 3 is 24. And in here, I will end up getting, let me make sure I do this correctly, alright, 1/2. Please feel free to comment below if you do have any questions. I hope this helped you out.